Good evening, ma'am.
Good evening, Kavya. Am I audible?
Yes, ma'am, you're audible.
Okay. Have you revised the yesterday's class?
Yes, ma'am.
Any doubt from that part?
No doubts.
Nomenclature, you said that you will do yourself, right?
Yes, ma'am.
So today we will do VBT.
Yes, okay.
Okay. Valence, bond, yes. Well, if we were having the Werner theory, then what's the need of VBT? Tell me. Why we move to that theory?
Um, I don't know. No idea.
It was because Werner theory doesn't explain that we have coordination compound of only D block element, right? Not of S, P, and F. So Werner was unable to explain that why only some elements form coordination.
Uh,
Okay.
yes, ma'am.
Second drawback was we have studied that the bonds that are made in the coordination compound are directional,
Yes, ma'am.
right? But Werner didn't explain that why bonds have directional bonds.
Acha.
Also, he was unable to explain the magnetic property. We know that some of the compounds have magnetic property and some do not have. But Werner was unable to explain that which compounds have the magnetic property.
Yes, ma'am.
Also, the Werner didn't explain us that why the coordination compounds with coordination number 4 have two types of geometry. We have studied that with coordination number 4, we have tetrahedral and square plane, right?
Yes, ma'am.
But Werner was unable to explain that which compounds have the tetrahedral geometry and which compounds have the square plane.
Acha.
Okay? That's why we need to move to the valence bond. So what is valence bond theory basically? We have already studied the valence bond theory in covalent compound. Right?
Yes, ma'am.
So what happens there basically in covalent bond? We saw that whenever a compound is formed, basically, the valence orbitals of the central one. If I talk about that, I'm having CSO. This is a covalent compound,
Yes, ma'am.
right? So what we see there, that the valence electron of carbon undergoes hybridization
Yes, ma'am.
because it's the only the valence electron that participates in the bond formation. Inner electrons do not play a role,
Yes.
right? So the
Yes.
valence electron of carbon undergoes hybridization and then forms a bond with hydrogen. Is it so?
Ma'am, sorry, your voice is breaking.
I'm saying that the valence electron or valence orbital of carbon undergoes hybridization and forms bond.
Yes, the valence shell of carbon and hydrogen form.
If I say that the configuration for carbon is this one,
Yes.
right? So the outermost electrons where n is same is basically 2s and 2p, where n is 2.
Yes, ma'am.
So it was only 2s and 2p orbitals that will play role in bond formation with hydrogen.
Yes.
Correct? So what
Yes, ma'am.
happens there basically? 2 electrons in s and 2 electrons in p. Correct? So what
Yes,
do
ma'am.
they do? S, 2s and 2p are having different energy,
Yeah. So they will mix
right?
and form a new orbitals.
Yeah, so they will undergo hybridization so that
Yes.
all the orbitals should have the same energy.
Equal energy.
Will it form this thing?
Will it form?
This one,
Yes. Yes.
right? Because in this case, they are having different energy. But when undergoes hybridization, all of the 4 electrons will have the same energy,
Yes, ma'am.
right? As I'm having 4 hydrogens over here,
Yes.
like in coordination compound, what we have seen, I can say that the coordination number is 4 over here.
Coordination number, yes, it will be 4.
Right? So
Yeah.
if the coordination number is 4, it means that I need 4 orbitals to bond with.
Yes.
So now I'm having 4 orbitals, 1, 2, 3, 4,
Huh.
right? So I can say that the hybridization is sp3,
Yes.
right? So
Mhm.
this is the theory that we follow in covalent bonds.
Yes, ma'am.
Okay? In the same way, we do with coordination compounds. So what happens in coordination compounds basically, valence orbitals of metal, right? As in this one, the central one. And in this one, I'm talking about the metal. The valence orbitals of metal get hybridized so that the energy of all the valence orbitals get equalized. And then they overlap with the ligand.
Okay.
Getting
Yes.
any doubt?
No, no doubts.
If we are having a coordination, like in this case, na, I told you that the coordination number is 4. So simply I find the hybridization to be sp3. And if there is some hybridization, it means that there should be some shape of the compound also,
Yes, ma'am.
right? So
Mm.
in VBT, if my coordination number is 2 basically, then my hybridization will be sp and the shape will be linear,
Linear.
correct?
Yes, ma'am.
If my coordination number is 3, then it is sp2, shape will be
Tritonal planar.
correct.
Yes.
If my coordination number is 4, then hybridization can be sp3 or it can be
DSP2.
dsp2. If
Yes.
it is sp3, then the shape will be
Tetrahedral.
tetrahedral. And if it is dsp2,
Square planar.
if my coordination number is 5, then the hybridization will be
SP3D.
either it will be dsp3 or it will be sp3d.
3D.
If it is dsp3, then the shape will be square pyramid.
Okay.
You are having which board, CBSE or any other one?
Uh, Telangana State Board.
Oh. If it is sp3d, then the shape will be trigonal bipyramid.
Bipyramid.
Okay. As in CPSC, we study only when the coordination number is 4 or coordination number is 6. But in your board, I don't know that what coordination number you have studied.
4 and 6 only, ma'am.
4 and 6 only. But for
Hmm.
the competitive exam, you need to know that the whole one.
Okay.
Okay.
Hmm.
You know, if you know the basics that how to calculate the hybridization or how to find out the hybridization, then you
Hmm.
can find it for any coordination.
Hmm.
So in that case, this will be used that if my hybridization is coming out to be this one, then my shape will be. Okay.
Yes.
If my coordination number is 6, then shape will
SP3D2.
be SP3D2 or D2,
SP3.
SP, both
Octahedral.
having octahedral. Clear?
Yes.
Now we will do questions. Well, what VBT tells us basically, it tells us whether our compound is magnetic, correct? It
Yes.
tells us the magnetic behavior.
Uh-huh.
It tells us the hybridization.
Mm-hmm.
It tells us shape. And it tells us nature of complex, either inner orbital complex or outer orbital complex,
Yes,
correct?
sir. Yes, ma'am.
And what else is it tells us shape in a I think these two is the hybridization here. Yeah,
High,
these are
high spin,
4 things. Huh?
high spin completes, low spin completes.
Yeah. Nature of spin basic.
Yeah.
Okay.
Yes, ma'am.
Then, if I take first example, I'm having cobalt. What is the name for this compound?
Hexaamine cobalt 3 uh, chloride.
Right. So if I say that my coordination complex is this one,
Hmm.
correct? So
Yes.
in this case, my central metal atom is cobalt.
Mm-hmm.
So what is the atomic number for cobalt?
Iron cobalt 27.
27. It means 3D7. 4S.
Forester.
Can I write this one?
Yes.
If I find out the oxidation number, and it means primary valency for cobalt, what it will be?
+3.
Plus 2. Yeah. Actually, the
Yes.
last class I forgot to tell you something that whenever we represent a primary valency, na,
Okay.
in the Werner theory, whenever we represent a primary valency, we always denote it by dotted in the structure.
Okay.
So by
Yes.
seeing the structure, you can tell that how many dotted bonds will be there, that it means it will be the primary valency. And secondary valency is always made by the number of solid bonds.
Okay.
Okay, so you can tell it by this thing by seeing the structure.
Mm-hmm.
If it is cobalt +3, then my configuration will be 3D6.
Yes.
Right? Now, if I represent it like this, 1, 2, 3, 4, 5, 3D, 4S, and 4Q. Correct? Now
Yes.
I'm having 3D 6 electrons. 1, 2, 3, 6. Correct?
Mm-hmm.
Whenever we have any ligand of carbon and nitrogen, ligand that is having carbon or nitrogen in 99% case. Okay? These ligands are basically the strong field ligand.
SFL.
Okay?
Yes, ma'am.
You have any idea about that strong and weak field? That we will
Yes,
discuss in
ma'am.
the CFT. But
A
for
strong field
now,
ligand, they will pair the electrons, unpaired electrons.
yeah. So in 99% cases, the ligands that are made up of carbon and nitrogen are strong.
Yes.
So in this case, what I am saying that my ligand is ammonia. It is NH3 made up of nitrogen. It means it is a strong one.
Yes.
So what it will do? It will do pairing. If it will do pairing, then my configuration will be like this,
Yes.
correct?
Mhm.
Now, see, as my coordination number is 6, so I need 6 vacant orbitals to hybridize. See, when we were doing the covalent one, like in CH4, what I have made over there is this thing,
Yes, sir.
right? So I said that the hybridization will be sp3, having 1 electron, because in that case, I have to share the electron only, a single electron from hydrogen. That's why one electron of carbon and one from hydrogen that I can accommodate over here.
Yes, sir.
So I'm having 1 electron in the orbit. But in case of coordination compound, I have to take a complete pair of electron from the ligand to the metal. So I need a complete vacant orbit.
Mhm.
So are you
Mhm.
comparing that what is happening over here?
Yes, sir, I'm understanding.
So I need 6 complete vacant orbitals. So if I say that with the coordination number 6, my hybridization will be either sp3d2 or d2sp3.
Hmm.
So if I take this one, then I am having 1, 2, 3,
3, 4.
4, 5, and 6.
Yes, sir. D2sp3.
D2sp3. So my
Okay.
hybridization will be D2sp3. My shape will be
Octahedral.
octahedral. If my all the electrons are paired, means my compound is diamagnetic.
Mm-hmm.
If my compound is diamagnetic, it means it is low spin complex.
Okay.
Okay. As my d orbitals are inner one, right? D is coming first. Then I say that my orbital complex is inner orbit.
Okay.
If it is sp3d2, it means d2 comes after sp3. Then I will say that my complex is outer orbit.
Okay.
Got it?
Yes, understand.
In this formula, we can calculate the magnetic movement also. What is the
Mm,
formula for magnetic movement?
root n into n plus 2.
Yeah, the number of unpaired electrons. N is the number of
Unpaired electrons.
unpaired electrons. In this case, I am not having any unpaired electrons. So N will
Hmm.
be 0 and magnetic moment will be 0.
0. Diamagnetic.
But yeah, BM. BM, that is the unit of magnetic moment, Bohr magnet.
Yes, sir.
Correct. Now, I will give you some questions today to practice. Just
Okay.
do one by one. Okay.
Okay.
One question from VT definitely comes in your exam.
Oh,
Just do this.
sp3.
Have you solved one or
The second one, COC alpha.
how? It is sp3 shape.
Shape is tetrahedral.
And
It's tetrahedral shape. Then paramagnetic nature, high spin complex, and outer orbit complex.
well, when we have the coordination number 4 now, in
Uh-huh.
that case, we never say define that our complex is inner orbital complex or outer orbital.
Okay.
It
Only
is
for D6.
only for, yeah, it is only for when we have the coordination number 6.
Okay.
What will be the number of unpaired electrons in this case?
Number of unpaired electron is 1, 3.
Oh, great. Now do this.
DSP2.
Okay. Shape.
Shape is square planar,
Mhm.
and it is diamagnetic,
Mhm.
low spin complex.
What will be the number of unpaired electrons?
0.
Do this one.
DSP3.
Sure.
I think
Let's check. What is the atomic number for iron?
26.
Means 36. Rest
4s2. Mm-hmm.
is Fe.
Uh, s- Fe is 0.
0. So it remains 36.
4s2.
Correct. Yes. And 4. Correct.
Yes.
As it is carbonyl. So it is a strong field ligand.
Mm-hmm.
So A1, 2, 3, 4, 5, 6. S
Yes.
M I have to I need vacant S1. So I will shift these two electrons over here.
Ready. DSP3.
Right? D SP
3.
2.
Oh, sorry, 2. Ma'am, 3 now. Like,
Just DSP, sorry, DSP3. Correct. So it will be DSP.
yes.
Correct.
Yes, ma'am.
So these are the questions that in this way like that comes in from PBT.
Okay.
So basically PBT also has some limitations that it doesn't explain the color of coordination compounds because coordination compounds are colored in nature.
Uh-huh.
Right? It doesn't explain us about the strong field ligands and the weak field ligands.
Okay.
Okay? So here I told you about that carbon and nitrogen ligands are strong field ligands. Actually, it's a concept that comes from CF.
Mm-hmm.
Okay, so here we start with the CF. That is
Okay.
crystal
It's been clearing.
field here. What happens in this case basically? CFT is completely based on d orbit. Okay.
Okay.
As we can see that we have 5 d orbitals in dxy, dyz, dzx, dx square minus y square, and dz.
Z square.
Correct?
Yes, ma'am.
These are the orbitals that lie between the loops. If I say that I'm having x and y axis, it will lie like this.
Mm-hmm.
dxy. This one is dxy.
That's why. Mm.
If I say dyz, then it lies between the axis y and z.
Mm-hmm.
If I say zx, one more axis is there. That is like it up, comes outwards.
Okay.
It is like
Mm-hmm.
and the orbitals that are dx square minus y square that lie along the axis. Okay.
Yes, ma'am.
Well, what happens in this basically? These 5 orbitals, d orbitals, all have the same energy. They are degenerate.
Mm-hmm.
Okay? And these are the lobes basically where the electron density is maximum,
Yes.
right? So
Mm-hmm.
what happens in this case basically when a ligand approaches the d orbital, if we are forming a coordination compound in it means ligand is approaching. So whenever
Sorry.
a ligand, if we are forming a coordination compound, it means there is a ligand that is approaching the central metal atom.
Yes, ma'am.
So the ligand has the possibility that if I'm, so ligand has the possibility basically that either it will come from that side that is between the axes or it will come along the axis. It can have the possibility of both. Are you getting?
Mm-hmm. Yes, I'm understand.
Understanding? Okay. So
Yeah.
if a ligand is coming, ligand is also having electrons,
Yes.
right? And the d orbitals, if I talk about that, the lobes between the axes, and if I consider that ligand is approaching from this side, that is between the axes. So here electrons are there, and if a
Mm.
ligand is coming, ligands also having the electrons, then will there be any repulsion between the ligand and the orbital lobe,
Yes, there will be repulsions.
right? So
Mm.
this is the reason that when a ligand approaches the d orbital or the metal atom, if it
Mm.
approaches from this part, right, lobes between the axes,
Oh,
then there will be repulsion between these lobes and the ligand,
okay.
right? And these will remain as such. So there
Yes.
will be something that will remove the degeneracy. Like these will have the repulsion and these remain as such. So their energy will increase and there will remain as such. Can I say
Oh,
this thing?
yes, ma'am.
Right? But if a ligand approaches along the axis, now what will happen in this case? Then the energy of these two orbitals will increase and theirs remain as such. Can I say this thing?
Yes, ma'am.
This is the concept that happens in crystal field theory.
Okay.
Okay. Whenever we talk about octahedral, only two cases are there that you have to study. One is the octahedral one and other one is the tetrahedral. What
Okay.
happens in case of octahedral? In case of octahedral, ligand always approaches along the axis. Got it?
Yes, ma'am.
If a ligand is approaching along the axis, if I say that I'm having d orbitals, degenerate d orbitals, these are my 5d orbitals that are these, right?
Yes, ma'am.
If a ligand is approaching along the axis, then energy of these two orbitals will increase,
Yes.
right? So among these 5, the energy of 2 will increase, that are dx square minus y square and dz square. Can I write this?
Oh, yes.
The energy that, how much energy is increased? So that much energy is decreased over there to compensate or to make the total energy neutral. Can I write it like this?
Yes.
These two orbitals, dx square minus z square and dz square, combining together make a EG1. We call these orbitals as EG orbitals.
Okay.
And these 3 orbitals we call as T2G orbitals.
Understand.
Understand me? The
Yes.
level where these orbitals are initially, we call this as barycenter. Basically, it is the reference. We call it as barycenter. Getting
Yes.
the energy that is increased from barycenter is basically 3 by 5 of delta naught.
Uh-huh.
And the energy that is decreased basically 2 by 5 of delta.
Okay.
Now, what is delta naught? As we are considering this case for octahedral, that's why we represent delta O. O represents octahedral. So, what is delta naught? Delta naught basically is the magnitude of splitting between T2G and EG.
Okay.
That we call as crystal field splitting energy.
Yes. Still feels like
Getting that what is happening over there?
yes, understanding.
Understand. Well, this is the case for octahedral. Now, what happens in case of tetrahedral base? In case of tetrahedral, ligand always approaches between the axes. Getting?
Yes.
Again, I am having 5 degenerate orbitals. If a ligand is approaching between the axes, then the energy of the orbitals that lie between the axes will increase.
Yes. D8
Correct? What we call as it is a triplet one, so we call T2G.
T2. Yes.
And it is EG.
Yes.
Correct?
Yes,
It
ma'am.
is the same. That is the very center. Correct? As it is 3 orbitals. So the energy that will increase from very center is 2/5. In this case, I have written 3/5. As 2 orbitals were there.
Okay.
Okay. So it is 2/5 delta T because we are studying considering the case for tetrahedral. That's why I represent it as delta T.
Okay.
Okay. And the lower one will be 3/5 of delta T. Got it?
Yes, sir.
Well, what and the energy that is this one. This is delta T means magnitude of splitting in case of tetrahedral. Now, is your concept clear regarding crystal field theory?
Yes. Concept is clear, ma'am.
Okay. Now, one more thing is happening over there that in case of octahedral, we represent as T2G and EG. In case of tetrahedral, we only represent T2 and E. Never write G with it.
Okay.
Because
T2.
what happened?
Nothing, ma'am.
Because G represents G rent.
Okay.
G rent is basically symmetric. And tetrahedral itself is symmetric one. Tetrahedral geometry is a symmetric one. Now, whatever be
Yes,
the
ma'am.
root we write, then it will always give the
It's symmetry.
same one. So that's why we never say represent it with G. We always write T2 and E.
Okay.
Okay. Well, the magnitude of splitting of tetrahedral is always less than that of the magnitude of splitting of octahedral.
Okay.
Yes. So delta T is equal to 4/9 of delta naught.
Okay. Hold on. Okay.
Got it?
Yes, ma'am.
One thing that we know from this, now we know the concept, we got to know the concept of strong and weak field from this part. What we see in case of octahedral one, basically, we have this type of configuration. In case of octahedral, right?
Yes, ma'am.
So If I have the D1 configuration, this means only a single electron in the D. So I will write it over here,
Lower energy.
right? Then I can
Yes.
write the configuration will be T2G1. For D2, I can write it as like this. For D3, I can write it as like this. Correct?
Yes, ma'am.
But whenever it comes for D4, I have the possibility of both. That either I can fill my electron this way, dash portion, or I can write my electron over here,
Yes, ma'am.
right? So here comes a concept of strong and weak field. What it says basically, if my compound is here, there concepts that is a pairing energy. A new concept called pairing energy comes. What pairing energy says that the amount of energy required to pair up the electron. If I need to fill my electron over here, it means I need to give some energy that is called pairing energy to pair up this. Getting?
Yes, ma'am. Understanding.
So now I am having pairing energy. One is delta, that is this one. Got it? So if my delta naught is greater than pairing energy, then I will do pairing. Means my electron will come over here and my D4 configuration will be T2G4. Getting?
Yes, ma'am.
But if my pairing energy is greater, okay, then no pairing will be done.
EG1.
Then my configuration will be T2G3 and
Hmm.
EG1.
Okay, ma'am.
Getting? So
Yes, ma'am.
there arises new thing that I'm having the two configurations over here. So from this concept, we said that the having compounds having low pairing will be strong field ligand. Can I write this thing?
Yes, ma'am.
Because the strong field ligands undergo pairing. And those having high pairing energy will be weak field ligands.
Okay.
Got it?
Yes, ma'am.
So basically, this is the concept for CM.
Okay.
In this, if you are having a particular doubt, then you can please ask.
Ma'am, some questions may they asked energy in numbers also, right?
What energy numbers?
Well, like 0.6 into 0.4 something. We have to multiply and tell the energy.
0.6 and 0.4 is basically this one. If you solve it this one, na, you will get 0.4. From this one, you will get 0.6.
Acha. So like some question may like in back in my offline institute, they were asking some us to compare these energies between the compounds.
Okay, that we will discuss. These are basically the stability orders that depend on the energy. It means you will be given some compounds and they ask you that whose energy will be more, whose energy will be less,
Ah,
will be the most stable and the other.
yes, yes, ma'am.
Yeah, this we will discuss. Till
Okay.
now, in this part, if you are having any doubt.
As of now, I have no doubts.
Okay. Well, one thing we have discussed that delta naught is greater than delta T, right?
Yes, ma'am.
But when relation that you have to learn also that if we am having a square planar form, it's not in your syllabus, but sometimes can be asked in the exam. Then my order will be that the square planar complexes have the maximum splitting energy, then octahedral and then the tetrahedral.
Okay.
This you can learn from spot of SP of spot.
Okay. Yes, ma'am. Ma'am, your voice is not clear.
I was saying that first we will discuss about the stability order.
Ma'am, I still cannot hear you.
Now getting
Yes, ma'am. No.
well. The stability of the coordination compounds depends on, initially, first point is the nature of ligand.
Yes, ma'am.
If when it applies basically, if I have the same metal and same coordination number is there, only ligand differs. Then how we can define that what will be the, which compound will be the stable one and which one will not. Okay.
Yes,
So
ma'am.
more the value of delta, more will be the stability. Can I
Okay.
say this thing?
Yes, ma'am.
Okay. And what I've seen there, that the strong free ligands basically have more delta or less delta. More strong free ligands have the more delta, na?
Yes.
Strong,
Yes, ma'am.
right? It means the ligand strength. More the ligand strength, more will be delta and more will be stability. It means
Yes, ma'am.
strong free ligands have the more ligand strength.
Yes.
Can I say this thing?
Yes, ma'am.
So one thing is this, when you apply this one, when you have the same metal atom with same coordination,
Okay.
like if I am having these compounds, this case, what I can see that all of them have the same metal atom, that is the iron, with coordination number 6 and oxidation number +3. The only difference that is lying over here is the central is the ligand,
Yes.
right? So if I say I'm having cyanide, I'm having water and N2, NO2, sorry,
Yes.
right? So I have told that more the ligand strength, more will be delta, and more will be delta, more will be stability. So among 1, 2, and 3, which will be the strong
Most
free
stable
ligand?
CN6.
CN1, na? So 1 will be more stable. Then comes
Yes.
to NO2.
Then two.
So this is the stability of.
Ma'am, how do I compare between CN and NO2? Like both of them are strong field ligand, right?
Yeah. This you learn from spectrochemical series.
Okay.
There is a spectrochemical series basically. There is a series like you have the metal reactivity series now.
Yes.
In the same way, we have the spectrochemical series for coordination. And from that series, we get to know that cyanide is the most strong field.
Okay.
Like cyanide, and from cyanide, carbonyl is the most one. Initially, we have the iodine. Like,
Yes, sir. Okay.
okay. From this series, you will get to know that among cyanide and nitro, right? Nitro, which one will be the most?
Okay.
Okay. Well, these type of questions you were asking.
Yes, ma'am.
Okay. Next is when we have, depends on the charge, oxidation number of central metal ion. When we apply this, if we have same metal same coordination number and same ligand. Only difference is the oxidation number of metal is different. Means central metal atom के ऊपर जो charge है वो different.
Yes, ma'am.
Okay. Then more will be the charge. More will be the oxidation number. And more will be the oxidation number. More will be the kinetic
Delta.
energy. And if delta is more, then stability will be
More.
4.
Okay.
Okay. When we apply this one, when there is a difference of charge on central metal. Like if I am having this one and this one. In this case, what is the oxidation number of this one?
+3.
In this case,
+2.
+2. So this will be more stable than this.
Okay.
I have this. +4.
+4.
Plus?
Ma'am, left one is +2. Left one is +4.
This one is +4. This one is
+2.
right? So
Yes,
which one will be more stable?
left one.
Correct?
Yes, ma'am.
Is this concept clear?
Yes, ma'am.
Next, we have basically the geometry difference. If I this one. Central metal atom is same.
Yes.
Oxidation number is same.
Yes.
Right? So one we can detect the stability from by seeing the ligand, as there is a different ligand. Cyanide one will be the most stable.
Yes.
Correct?
Yes,
One we
ma'am.
can see from this side. Other we can detect it from geometry. If I say I am having nickel chloride, then the hybridization of this one will be sp3, and for
sp3.
this one it will be dsp.
dsp2.
Okay. It is tetrahedral. It is square plane. I told you the order now that delta for sp will be greater than delta naught and then delta.
Yes, ma'am.
Its delta will be higher, more will be the stability.
Yes, ma'am.
Okay. Next we comes to chelation. The complexes that form chelate compounds, means that form ring basically. These will be more stable. Ring formation means stable.
Yes.
Okay. If I say that you are having this compound, you are having this one. See, one you can check from that my ligand is a strong field ligand or weak field ligand. If my central metal atom, coordination number and oxidation state all are same,
Yes.
right? So En is a strong field ligand.
Yes, ma'am. Relatively.
So one we can check from there. And other we can check it from there that En is a bidentate ligand. That is ethene 1 diamine. So it forms ring. Right?
Yes, ma'am.
If it is forming ring, then it means it is a chelated compound and this will be more stable.
Okay.
Got it? Basically,
Yes,
these are the terms or the concepts that we have from stability.
Now I'm like, it's in the same question, last one, ma'am. If it was NiCN sets instead of NiH2O sets.
Then this one. Huh?
Yes.
What will be the charge?
No,
Same.
and -4 +2.
Yeah. Then this will be more stable.
So chelation is over Stonefield legend also.
Yeah.
Okay.
Clear?
Yes, ma'am.
Next, we have the color concept. After coordination compound, which chapter you want to study? Because I think this will chapter either complete in today's class or tomorrow it will take hardly 5 to 10 minutes.
No, after this, ma'am, block chemistry would be nice.
Block chemistry.
Yes, ma'am.
And apart from block chemistry,
Um, electrochemistry sounds fine.
so we will start with electrochemistry.
Okay.
Electrochemistry you also want from the basics.
Yes, I'm electrochemistry. Mine, it's not very well.
Okay. Then we come for color of the coordination. Basically, what happens in coordination compound, there is a term that happens, that is the DD transition. What is DD transition? When we say see CFT now, what we see that EG and T2G splits into two levels,
Hmm.
right? So if I'm having one electron over here and I'm
Hmm.
passing some energy from this side, what this electron will do, it will excite to this part.
Yes.
And whenever
I,
it uses the energy that it absorbs, it again what will do? It comes back to its original position.
okay.
Whenever it comes back to its original position, it loses some energy,
Yes.
and that energy is basically responsible for color. So whenever there is a presence of D to D transition, only then the electron will come back to the original position, which is energy.
Okay.
Okay. See what is happening there. If I'm having any D block element, like if I'm having iron. So in iron, what I can see that all the d orbitals have the same energy. But whenever any ligand approaches, only then the degeneracy of d orbital is removed. So in this case, we can say whenever a ligand approaches the central matter, only then the degeneracy is removed and there will be DD transition. So DD
Okay.
transition always takes place in presence of ligand.
Okay.
Okay? And the color that is absorbed basically and that is seen. As per the gray scale, the sum of absorbed color and the seen color always gives us white and black.
Oh,
Got it?
yes, sir.
Like if I'm having the example for titanium. If you are having this one and you are having this, which one will show the color code? This one or this?
Left one.
Yep. It will not show color because in this case, degeneration is not removed,
Yes.
right? So for titanium, what is the oxidation number? 22.
Uh,
3D2
32.
4s2.
Yes.
It is 3D1 as it is an octahedral compound. So my
Yeah.
splitting will be like this because the coordination number is 6. If it is 4, then I will write 3 over here and 2 over here.
Uh-huh.
Right?
Yes, sir.
You can remember this from this part. Na? If it is 4, then it will be tetrahedral. And for tetrahedral, T will be up.
T up, E
For
down.
tetrahedral. T up for tetrahedral and vice versa for octahedral. This is the
Yes.
trick from by which you can learn.
Yes, sir.
Okay? So there is one electron only. So it can over here. So
Hmm.
as it is a single electron, it has the possibility to go upwards by absorbing the energy. So it will undergo KT transition and impart color.
Yes, ma'am.
Basically, this is the concept of color coordination. Here
Yes,
your
ma'am.
chapter has been completed.
Okay.
Any doubt you can ask.
No doubts, ma'am.
Now, are you having confidence regarding CFT or still have in dilemma that
No, no. I have a more confidence like now.
just try to do more questions?
Yes, ma'am.
If found any difficulty, then please ask.
Sure. Yes, ma'am.
Okay.
Thank you.